So, hello everyone. If you're watching this, well, you didn't miss anything because everybody was in class today. But in case you wanted something to refer back to, this is our lecture on unreasonable time, which was given on the 2nd of March. Let's go ahead and get to it. So, we talked about linear time and we talked about logarithmic time in a previous lecture. If you need help with those, please refer back to my previous video. Today we are talking about unreasonable and polynomial times. So what are those things? How do they differ from the two we already discussed? There are some assignments that are approaching their deadlines. Please make sure that if you are in an unfortunate boat of not having done these yet, you put forth an effort and turn in something by the deadline so I can at least give you 50%, if nothing else. So traversals make, deadline is March 4th. Hackathon project, deadline is March 10th. And then the small little exit ticket we did last week, if you didn't finish that, the deadline is March 15th. All right, let's get going. So what does it mean to say one algorithm is more efficient than another? Well, of course, a more efficient algorithm has fewer steps. Now, suppose you have two lists. Suppose we have two different ways to traverse a list. Well, I want to know which one is more efficient. Let's imagine they somehow accomplish the same task, although that's highly unlikely given the way these are set up. What I want to know is which one of these has a faster runtime. Well, hopefully you've paused the video and thought about it. So let's kind of think about it mathematically. Option 1 here has two loops, one inside the other. Call them nested loops. We would like to know how fast this runs. Well, the outer loop, we recognize that as regular linear runtime, right? It runs for as many times as there are elements in the list. We don't know how many that is, so we'll say that is big O of n. Hopefully that makes sense. It runs n times. What about this guy? Well, this guy's a little weird, right? First is going to run 0 times. I is going to be 0. 0 is already not less than 0, so we're done. But we can keep going, and we can do this the second time. It'll be 1, then 2, then 3, then 4. So ultimately, it's going to be, 0, then 1, then 2, then 3. We're going to have to add these up. So as our final sum, and this is going to keep going, the final kind of runtime of this whole thing is going to be both of these guys together. So n is the number of times we're going to do this, and this is going to go from 0 all the way to eventually n. So really the runtime of this thing is going to be, well, to be exact, it would be something like n plus 1 divided by 2 times n, but all of that is irrelevant. What we're really going to care about in this class is what is the fastest growing term. This is going to end up something like big O of n squared. So it's going to go all the way to n. N times n is going to be n squared. Hopefully you see my logic there. This is technically going to go to n minus 1. Over here on the right-hand side, what do we have here? Well, we have an outer loop that's going to start at the list length and then keep getting cut in half. Whenever you see something getting cut in half, you should be thinking to yourself, O of log 2 of n. Pretty fast. That's exciting. What about on the inside here? Well, on the inside, we have just a regular linear approach, O of n. So what does that mean for our sum, for our total speed here? Well, hopefully you guys see the pattern here. We're going to multiply these two together. You're going to get something that is O n log n. And n squared is much, much slower than n log n. So this one is a little bit less efficient than this one. There you go. Now, if you thought this one was more efficient, not the end of the world. These are pretty similar. They're not that different from each other. The difference can only be seen in really large numbers. So we are going to explore these kinds of questions in much more depth starting next class, and you're going to start off with much easier examples. This is a much more advanced one. So we just did this one as a warm-up for me to go through it with you and kind of show you how to do something like this, and next class we're going to expand upon this knowledge. All right. As a review, remember, a binary search gives you this kind of complexity, whereas a linear gives you this kind. And as n becomes larger and larger, binary search is going to be much, much more efficient than a linear search. Now, some reviews for assignment 517, which was the hackathon project. Reducing complexity. When we talk about that, what I mean is, how does a particular programming construct, like a list, give you as the programmer more freedom and ease of life while you're coding? Not how does it change something for your computer, not how it changes something for the user, but for you. How's having a list making it easy for you to imagine and design your program? That's what I'm focused on. You should be talking about how, well, you'd need 1,000 individual variables otherwise, and that would be really cumbersome for you to keep track of. The computer wouldn't really care. The computer doesn't care whether you want to store things in variables and have a bunch of them or a single list. It's all the same as far as the computer is concerned. What's changing is your understanding of the code, not the computer's. What's the point of filtering? So some of you guys, sadly, did something like this. You stored a list of some kind from a column. So far, so good. You made another list. Okay, sure. And then you used a for loop to take every element of one list and put it in the other. Why? What's the point of doing that? There is no discernible reason I can find where that would be a useful operation to do. Why not just say other list equals some list? That does the same exact thing. It's faster. It doesn't have a loop. So some of you thought that if you just put a loop somewhere in there with a traversal that did absolutely nothing for your program whatsoever that was meaningful, you'd get the points. But no, it has to actually do something for your program. So your filter must either search, sort, or process your list in some way. If you just put it out there and we're like, hey, I did one, no, you're not getting credit for that. So please go back and rewrite it if you were one of the people who did that. And last but not least, the final problem I'd like to address is in the exit ticket. A lot of you guys, when asked about binary search, correctly identified that the list needs to be sorted. That's right, the list does need to be sorted. But then you went on to say, in order to do a binary search, your list has to have binary values. Huh? What's a binary value? A binary value is a 0 or a 1. Why are you searching a list of zeros and ones? All you can find is a 0 or a 1. Seems pretty pointless to me, so I would posit that you probably don't want to search a list of binary values. Seems like a waste of your time. You'd rather search a list of words or a list of numbers, not binary values. So please go back and take that out. If you put that in, that is not correct. All right, for our class activity today, we used this ticket generating widget. We got a ticket. And then, similar to last time, we tried to get a winning number, but this time, you didn't play by yourself. You had to go and find one other person and combine together your numbers needed to add up to the winning number, which was 1,000. So obviously, this is a little bit more difficult because now in order to find the winner, not only do we have to check every number, but we have to check every combination of two numbers. That's a lot more computation to do, right? Think about it. If there's 30 people in the class, we'd have to check one person against the 29 others, then the second one against the 28 others, and so on and so forth. It would take a really long time. Then we made it even worse. Now we said, pick another ticket, use that ticket along with any number of other tickets to get to 2,500. Well, now the problem is immense. Think about it. Not only do we have to check every group of 2 tickets, now we have to check every group of 3 tickets, every group of 4 tickets, even every group of 30 tickets. There's only one, but we'd still have to check it. So there's way more checks. How many more checks? Well, it turns out that the pair raffle is something we call polynomial time. As the number of tickets increase, the speed at which this graph grows is some kind of n to a power, n to the 2, n to the 3, n to the 4. So when we talk about big O, we're only really interested in the fastest growing term. In this particular case, that would be n squared, similar to how in our warm-up over here we said, well, this is close to n squared, even though there's other things going on here. The thing that matters most is what's going to be happening way, way, way out there as n gets really large. We say this is our cutoff. This is the slowest time that we're willing to tackle in terms of problem solving. Anything slower than this is going to be too difficult. What might be too difficult? Well, the group raffle, for instance, we call this exponential time. This is 2 to the n. The n is in the exponent. When you have something to the n, it's too slow to even attempt usually. These problems are immense. They become quickly unmanageable for any meaningful data set. What do I mean by that? Well, first of all, these guys are all reasonable. We can work with these. Even polynomial time, we're not excited by it, but most computers can do this for really large data sets. Exponential, we call these problems unreasonable or intractable. We do not tackle these, they're too slow. How slow? Well, if we look at our sorted raffle, 17 checks for 100,000 participants, that's so easy. Linear sort, so n time, 100,000 checks, no problem. A computer can chug right through that. Polynomial time, that's a big number, but even that larger number is not really too big a deal for a computer. It might take it a little while, but it'll get there. When we talk about the group raffle, the number is so ungainly so quickly that just at 1,000 participants, we would need more checks than the number of atoms in the universe. That is a mind-boggling amount of checks, and we can't even imagine that. So exponential time is right out. Now, at the end of this class, I showed a video. I highly recommend you go and watch that video. It is right here. P versus NP, Computational Complexity Zoo. You can also find it on YouTube just by typing in P versus NP. It's the first result you'll hit. This is a fantastic discussion about P and NP groups, and I just highly recommend you go and watch it. This is a mind-provoking, or thought-provoking rather, very interesting piece of informational, educational cinematography, and I highly encourage you to check it out for yourself. At any rate, next time we're going to be covering the traveling salesman's problem, which actually is one of these NP problems, and we're going to see why it's so tricky to solve. Have a great rest of your day. If you have any questions, please send me an email, and I'll see you later.